So I'm not referring to a particular problem, or actually, Martin, you might have the number, but there's a z squared in front of it. So I'm going to change. I'll write the problem. So
loosely related from 1.31.
Okay. So this is related to 131. So you have a surface. So this is the x, y, z plane, and I picked for ease, and I think this may be the one on the book too. 0, 1, 0, and 0, 0, 1. So all three corners of the x, y, and z axis have 1 unit length. So the area that, or the volume that we're considering, is the volume bound by the xz plane, the xy plane, the yz plane, and the slanted surface. And in the actual question, what did they want you to find, Martin?
The vector was z squared.
Z squared? In what, is it a vector or?
So it's t is equal to z squared.
Okay.
Yeah. Over the function. Just
and find the volume integral, right?
The volume integral.
Yeah, so the difficulty in this, d tau again, this is peculiar with Griffiths, it's volume integral. The only difficulty is z squared, we know how we can integrate nicely, is to find the bounds of these objects. And there's much to be learned from that. So what I will do, I don't wish to do a longer calculation, it's just longer by algebra. I just have to square everything, yeah? So I don't want to do that. What I'm going to do is simply d tau. I'm going to find the volume of this object. If you do the exact same thing, you can just put that in. Okay, fine. So as Martin has correctly deduced, the whole entire difficulty is finding the limits of integration. D tau, as you know, in Cartesian coordinates, I mean, this is begging for Cartesian coordinates. Yeah. It's dz, and I'm writing it intentionally this way, because that's how I'm going to, it's dx, dy, dz, doesn't matter. I'd like to, if we have choice, I'd like to think of x as the independent variable, okay? Fine. So I have to worry about limits of integration. So x, what I'll do is I'll make it the independent variable, and I'm going to integrate it all the way from here to here. That's easy. So the x integral is going to be 0 to 1. I'm not doing any integration yet. I'm just sort of writing the limits, and then it's just a trivial matter. Now, y, for every x, I don't go as far out as this. I go as far as, I go this far. Correct?
Wait, can you say it again?
So now the question is, for any x, right? What will be my limit of integration for y?
Oh, you only go to that
Where the boundary ends.
Okay.
So let me just maybe even pick a different color if I'm able. It goes this far. Okay? So to understand how far this is, let me draw my y-axis temporarily like this. This is my x, this is my y, and I hesitate to use blue because I've been told it doesn't show up. But what I'm going to do is, you see it as I do it. You see this line? I'm going to draw it like this. From 0, 1, 0 to 1, 0, 0. Just so that I know how far I need to go. And then this line that I have drawn here is simply, again, being consistent with color, is that line. Do you see that? Okay. Now this is a simple line. It's y equals mx plus b. What is the y-intercept? 1. What's the slope? Very good. So then my y-integral will have 0 to 1 minus y. That's as far as I go. Sorry, 1 minus x. Now you need to know at any point over here, how far up do I need to go on the z-axis? So I need the equation of a plane. What will the equation of a plane look like? Well, let's think of a simple plane. XY plane. What's the equation of the XY plane? It's a set of all points satisfying what equation? Huh? The XY plane. Z equals 0. That's the XY plane. What's the YZ plane? Well, it's all the points satisfying x equals 0. So the point is, a complicated plane in general, the equation of a plane is given by some constant plus times y plus some constant a times x. A is a constant, b times y plus c times z equals d. Where a, b, c, and d are what? In the case of the xy plane, it's z equals 0. That means a and b and d is 0, c is 1. If you want the plane parallel to xy but located at z equals 1, well, that is z equals 1. That means d is 1, c is 1, this is 0 and 0. But a more complicated angle, it's still a linear equation. Yeah? Planes are effectively two-dimensional lines. Yeah, so it's a linear equation. You won't get a quadratic term. If you put a quadratic term, like x squared or something like that, things are going to curve like a hyperbola and a parabola, and so on and so forth. So this is the general equation for a plane. Well, that's fine. But we want to find the plane that passes through these 3 points. Well, that's easy. I'm going to pick the first point. So I get A times 1, 0, 0 equals D. Correct? Fine. So I'm going to write this as A equals D. Well, you know what's going on. Similarly, what do you have from the other one? I can do slightly better. So I write it as AX, nope, I write it as DX. I'm going to pick everything to be D, dy plus dz equals D. That's too many D's. Well, now I have my limits of integration for for Z. I start from the bottom and go to this is really the only tough portion, but now that I've gone this far, I'll carry out the integral. So these are the difficult parts of the problem. Make sure, because I chose x as my independent variable, these are the limits I get. I could have picked y as the independent variable, z as the independent variable. Just a creature of habit. Okay, well, let's. So literally what I'm doing is I'm finding the volume of the sucker. That's what it is. So because I've changed the problem itself, I hope you have the inside cover of your textbook. I'll be freely using it, so you'll miss out on where it all came from. Carry it with you. I saw a student walking down the hallway I overheard the conversation. She says the price of tattoos has gone up, and so she's not quite sure if she should get a tattoo. If you're going to get a tattoo, get the inside cover of Griffiths.
Would that be cheating?
No, it is not. It is allowed in the exam. So I'm going to do dz first, and I go 0, 1 minus x plus y. Then I'm going to do dy, 0, 1 minus x. And then I'm going to do dx, 0 to. All right, so I'm going to do the first integral first. Integral of z dz is just z. Now if you're doing the other problem, you would get z squared dz, so it'll be z cubed over 3. I just didn't want that cube. So then I simply get 1 minus x plus y dy dx. I already put the limits. When z equals 0, it's just 0. So 0 to 1. Let me simplify this slightly. 1 minus x. I'm going to write this as 1 minus x plus y dy dx. 0 to 1. 0 to 1 minus x. I integrate y. I would get 1 minus x, which is a constant, times y, plus y squared over 2. And then I put the limit y equals 0 and 1 minus x dx. Oh, not d. Yeah, dx is the only one that remains. When y equals 0, again, the lower limit vanishes. So I get 1. Oh, I made a mistake.
What happened over there? I think you missed it.
Yeah? Good, good. 1 minus x squared minus 1 minus x squared over 2 dx. And that's 1/2 0 to 1, 1 minus x squared dx. Please make sure that I'm not making a mistake. 0 to 1, 1 plus x squared minus 2x dx. That is equal to 1/2 x plus x cubed over 3 minus x squared, going from 0 to 1. It's 1/2 1 plus 1/3 minus 1. I don't know if this is the answer, but it looks good. Any questions? Feels like a Calculus 3 class today, huh? James, which term is confusing?
Just the second one to the third one.
Second to third?
Yeah.
Apple minus half an apple is the remaining half an apple. Apple minus half an apple is the other half of the apple. Yeah? Okay, you've had 2 chunks worth of E&M. By the time we get to the 5th chalk, I bet it's a hot mess. Good, everyone? Okay, so what I'm going to do is I'm going to begin by doing problem 1.61. And there's a reason for it. I'm going to get to problem 1.62. So 1.61, I think I've assigned the whole thing. I'm going to do part A. You should do part B and part E. Okay? Not more, not less. It's exactly the same technique that I'm going to employ. We're going to use a certain trick, and then we're going to deploy either divergence theorem or Stokes theorem. That's it. Okay. And they've given you the hint as well. So let me write the problem down. So I'll write it down. Problem 1.61, part A. This is from Griffiths, of course. And the problem states, show that this is true. So I take the gradient of some function and integrate this along some volume. And then, so now you can see this is sort of begging for divergence theorem. I've started out with a volume. And especially if it ends with a dA. And indeed, it does. The surface, which is the boundary of that volume, T times dA. Look at this. This is a scalar volume. This volume has no direction. This is a vector. So when you integrate a vector, you better get a vector. And it's this vector, dA vector, okay, for any surface. So they've given you a hint. So hint. You define a vector V that's equal to T times some constant vector. And then use the divergence theorem. Okay, the hint makes our life much easier. So that's precisely what I'm going to do. Oh. that's a big integral, son. That's not what I meant to do. Although, that could be my signature partition line. Okay. All right, so I'm going to do divergence theorem because I don't know what else to do. And then, with the divergence theorem, I'm going to replace it. Is the divergence of a scalar function times a constant vector. You know from the inside cover, this is gradient of t dot c d tau plus t times, again, this is all volume integral, t times divergence of c. I think if I'm wrong, you're on your own. So again, let me make sure I'm using property number 5 and I'm correct. But c is a constant vector.
The constant vector is just 1, 2, like just 3 constants.
Yeah. So c is like 2x hat plus 3y hat, but you can pick any number. So, but if you do the divergence of constant coefficient, you're not going to get any. Yeah. So I get this, and I'm going to write this as c dot gradient of t, gradient of t d tau. Because again, c is a constant, so when you integrate it, you don't have to worry about it. And you can bring it component by component. Cx x hat, cy y hat, cz z hat. So you get that. All right, that's one side of the divergence theorem. But what do you know about the divergence theorem? Divergence of v d tau equals what? V dot dA. And that's simple enough. That is c t. Nope, sorry. T times c dot dA, that's equal to c dot t dA. This, of course, is the boundary, the surface. So what we have shown is c dot This is not true for just one C. It is true for any constant vector C. In particular, you can pick the x component. C can be just x hat. Yeah? Correct? So then the x components are equal. Then C can be y hat, then the y components are equal. Then C can be z hat, the z components are.
That first statement is just divergence theorem definition, right?
From here to here, it's divergence theorem. And then I'm replacing V with T times C.
So
This is true for every C. If it's true for one C, then this is not true. True for any C. Therefore, I can remove the C hat. Remember, again, what I said, I'm not going to write it down, I'm going to write it as end of proof. Okay? Which,
this might not be too relevant, but why did you use that closed surface integral for that first statement? Like the first divergence theorem definition?
Yeah.
It's supposed to be the closed surface integral.
Yeah.
I just didn't know.
Yeah, no, fair enough. Yep, yep. Again, truth be told, I need to put volume, just to make sure. And that's the boundary, so volume, C, oh, this is not true. This is the volume integral. So you understand the argument? This is true for any vector C, therefore it is true identically, meaning this is true. Because I could do this as x hat, then x hat components agree. Then I can do it for y hat, then the y components agree. Then I do it for z hat, and therefore it agrees as a vector. Yeah? So this is not hard to do, it's just that you have to, in this case, he gave a hint. When the hint is not given, all bets are off, kind of thing. Okay? Any questions? You're still staring at it, so I'll let you.
So
this is what we have shown. This is in passing. We don't need to commit this to memory at all. But do put a sticky note on problem 1.61 and 1.62 so that you know when you have theorems that are not Stokes' theorem and divergence theorem, but they look like integral theorems, come to problems 1.61 and 1.62 and just use the equations blindly. They follow. Yeah? They're taking divergence in Stokes' theorem and letting you play with it. But it becomes handy. Okay? So the next problem I'm going to do is 1.62, I think part E. That requires that you know 1.61 part E. So having done one of the parts of 1.61, I'm assuming that you will complete the others, in fact only B and E, should you really try. And so I'm going to assume part E of this problem. I'll write it down. But then let me write down what it is that I'm trying to do. So first of all, let me define an area vector. Suppose you have a surface, not dA, but rather A. You can imagine what it is. It has some nice properties. It really doesn't always mean total area. So the area vector so suppose you have a surface, yeah? The area vector is simply, it looks trivial, but it's the integral of the dA. Now recall again, what's dA? It's a small differential area, but the direction is what? Normal. And once again, this is only defined up to one choice of normal. That's fine. If it's a closed surface, it's easy. Pick the outward normal.
You said this was problem 1.62, right?
I'm defining the quantities in problem 1.62. So the things that you should do, and I'm going to do the difficult ones. And I got news for you. I'm not going to assign these problems in the test. Okay. So I would like for you to do part A and part B. What I will do are parts D and parts E. So, sorry, parts D and E. Those are the difficult ones, and I think we'll need part D in chapter 5. Okay. And I just like to do proofs, so it's good to have this list. But this is a curious thing. I've asked you to do part B. Part B says, if you have a closed surface, the area vector is 0. So do not think of area vector as some weird direction in the total area of the surface. If you do it for a sphere, the area vector will be 0, because for every area in this direction, you're going to get an opposite area. So do parts A and B. Let me do 1.62 part E. Let me state the problem first. The problem itself says, show that A cross C equals, is that what it says? Yep, that is what it says. C dot R DL. Now when you see a DL like this, you must realize that this is a closed. So again, while closed, if you have any area, the boundary is any area. The area is not closed, but the boundary is closed surface. So this is going to be so first of all, let T equals C dot R. T is a function I'm defining. That is C times the position vector. When I say R, what do I mean? That's what I mean. So let me first write problem. I'm going to begin with this result. Problem 1.61 part E, which now I'm assuming that you have done. It tells you that the surface, if I do this surface, so this is the surface, okay? This is my DL of gradient of C dot R, means this guy, cross dA, that is equal to minus C dot R dL. As I do this, let me confirm. Yep, that is exactly. So in part E, there's a function T. If I replace that function T with C dot R, I get this equation. We're taking this for granted. You will have shown this. So what I need to do is start from one side and go to the other side. Okay, so I'm going to start with this guy. It's the gradient of two vectors. And I'm going to use, where is it? Gradient, which am I using? Gradient A dot B, property 4. Now in property 4, there are 4 terms. two of which will disappear because I'm going to be taking derivatives on a constant vector. Yeah. Yeah, it just goes away. Yeah. So the remaining two terms, and if all of you had your inside cover with you, I'd ask you to verify as we go along. But when you go home, I would like for you to verify that the only two terms that remain is, again on the surface, C cross the curl of R plus C cross the gradient R, and then I have cross dA. That is just plugging in property 4. What is the gradient of this guy? I'm sorry, curl of R. X hat, Y hat, Z hat, partial with respect to X, Y, Z, X, Y, Z. Y, Z, 0, Z, Y, 0. Then for this guy, partial X of Z, 0, 0, 0. This guy is 0. Before I plug this equation back in, I want to simplify this guy. Okay, C, how did I write a vector Cx partial x plus Cy partial y plus Cz partial z acting on x, x hat, y, y hat, z, z hat. That's what this is. Yeah? When I act, so let's look at this guy first. When I act these two guys, it's going to give me 0 because I have only x here. So I get Cx x hat. When I do this one, well, that is nothing more than C. Huh, weird, huh? All of this trouble. It's a fancy way of writing C. And so what do you get? What did I tell you? This is not difficult at any stage, but it'll test your patience. Am I done? See, it's so convoluted, you forget whether the problem is done. So I have shown that this is that. So that means this is that. You want me to write it out? This is this. This is this. But look, this is the same as that. So this is the same as that. And that's almost the problem. This one, what's the difference? The negative sign. But I have C cross dA. What do I have over here? A cross C. So that minus sign goes away. I guess I could because integral of dA is just A. I don't think I can make, I can do the next problem. I'll just state it, and maybe I'll put a video up. Watch it if you care to. No promises, but I hope I can put something up. But I'll state the problem, because that's the result we need. And it's a tricky calculation. That's the one where, that's the problem where Griffiths want you to use approximations, and we won't. So I might put the proof out there. Is that clear? No part should be difficult, right? Really, I took a stack of paper and just started writing every equation back and forth and back and forth. After a while, you get a sense of what cancels and what doesn't cancel. That's it. Eventually, you'll become more and more patient, and the sooner you get there, the better for you. You'll have more Zen moments where you have toiled and obtained something. Toil is important for deep satisfaction. The worst circumstance to be in is to be a trust fund baby, right? If you are, you have to leave your parents and walk away like Buddha. He was a son of a king. He enjoyed life for a few decades and said, I'm done. So let me state the result, and I may put a video. This is part D. So part D. Yep. It's a nice formula for A. So let me sort of state what this is trying to say. Is suppose you're trying to find the area vector. So you might, first of all, your coordinates might be here. It doesn't matter where it is, but I wanted to show you that it could be just anywhere. And you have an area over here. DL, it's clear that it's going to be, let me do it, I want to have a nice angle. Let me first do it this way. This is my vector R, and this is my vector DL. So, I'm integrating this way. So if you again, look at how powerful it is. If you do things in the boundary, it tells you how much area you have inside. Huh. Well, that's curious. It's like black hole holography. You've probably heard the term, right? What goes on in the bulk really happens in the boundary of things. The boundary tells you how much area is in the middle. I could use, this is sort of like a soap bubble filament, right? Says who? What if I pick this area? The area vector will be the same. The area vector for a closed surface is 0. That means this area vector plus this area vector pointing outward is 0. So that means the area of this guy must be the area vector of this guy is the same as the area vector of that guy. Very powerful statement. Huh? In the future, when you study magnetism, magnets are made up of small magnetic moments, electrons just spinning around and forming current loops. And what you need is the current, the magnetic moment will depend on the area vector. So we'll just need this equation. So in particular, if you are a careful note taker, you should note that this equation will be used in section 5.4.3. I will remind you. Of the text. Yeah? I will consider chapter 1 to be complete. Depending on how much energy I have. Oh no, I broke my chalk. I might put a couple of additional material.